So, I couldn't resist writing the Snake Lemma. I've left the proof of the Snake Lemma to you. I will briefly kind of explain it, I guess. So suppose you have the commutative diagram of the exact rows. So these are like sort of almost or exact sequences. The defect here is F1 may not be 1-to-1 and H2 may not be on. This is actually a very important theorem in homological algebra. If you have these two exact rows and the diagram commutes, then you have an exact sequence, kernel, kernel, kernel. Right, that's the first three parts. I didn't tell you what the alphas are, but they're kind of naturally induced, right? Alpha 1 is induced by F, right? Something here to see where it goes to there. Make sure these are all well defined. Then also co-kernel, co-kernel, co-kernel for this set here. Well, remember the co-kernel, for example, co-kernel here is B1 mod, the image of G1. And the interesting part of the snake lemma is the snake. That is, how do you get from something in the kernel G of 3 and snake it back over to something in the co-kernel of G1? Well, if it's in the kernel of G, it goes to 0 here, right? Right, if it goes to 0 here, and it's certainly got a pullback here. Now, this pullback may not be well defined, but when you do the diagram chase here, this has to go to 0, which means it's in the image of this. And so pull back here, go here, it pulls back to here. And even though it seems like it's not well defined as an element itself, it's not, but it's well defined modulo something in the image of G. So you get a well defined element of co-kernel of G1. So that's the way the snake works. Snake your way back here to get an element co-kernel. So have some fun with that problem, actually. Let me give you kind of the next theorem. And this the proof of this is actually kind of one of my favorites. And this is where we this theorem I'm going to use to sort of as a launch pad, what I'm going to call split exact sequences. That are the ring and 0, A, B, C, a short exact sequence. The following conditions are equivalent. Number one, I'm doing here. There exists H and C B such that when you do H and G, yeah, and C, and H is normally only one of this. There exists K from B to A such that when you do F and K, get the identity function on A. And 3, the sequence above is isomorphic to and I'm gonna clarify what I mean by isomorphic. Well, A back to C. In particular, So B. So that's more for A sub C. Now, let me make a couple of remarks on this before we get too carried away. First of all, let me tell you what I mean by isomorphic. Uh, Isomorphic here means you say it this way. Means the diagram is. So you join up the head and tail of this in the obvious way with the identity functions. And there's some phi in here that makes this diagram big. The short five limit tells you that it is necessary, phi is if the diagram commutes, it's necessary that phi is an isomorphism. So short five gives these are 1 to 1, so this is 1 to 1. These are onto, so this is onto. And let me make clear here. So this is the projection from A and A comma 0, and this takes A comma C and just reads the same factor like this. Let me make another remark. I don't want you all to be misled. It is the case that if one gets all of these conditions whole, then B is isomorphic to the bookends, direct sum of the bookends. However, if B is the direct sum of the bookends, this is not necessarily good enough to give these conditions in general. I'll ask you for an example of that later homework. It's kind of fun. Your example has to be pretty big in certain sense. A two exact sequence that satisfies one, hence all conditions of 648 is said to split. Or sometimes I might say a split exact sequence. And these maps right here that go backwards and compose the identity, they're sometimes called splitting. Intuitively, also, it sort of means that you can run the exact sequence in reverse, right? Okay, so let's prove this. This is fun to prove. It also illustrates kind of a way to sometimes think about these things as well. first tackle this one. We're assuming the existence of the splitting here. And we want to find K. So we need to find, our goal, we need to find K beta A. Such that when you do F and you do K, it's the identity on that. Right, that's our version here. Well, we'll do this. We have H. When I do okay, now the question is, I mean, this is kind of big. How in the world am I going to assign an element if I start with some B here? What in the world am I gonna do this? Right, I mean, gee, I don't think it's clear at all. And of course, it's still up there, in general, can't. I guess we're gonna need something about the fact that this is a short exact sequence. We're probably also gonna need splitting. Under what circumstance, if I walk up to you on the street, and I give you a B and B, under what circumstance do you know that there's some A back here that goes to it? Well, right, but in this, yes,
If, let's see, if G of that B is 0,
that's right. So if I have some B here, it goes to 0 here, at least I know there's something back here that goes to it, and maybe it would make intelligent sense to take that B and assign it there. And that's kind of the thinking behind what I'm gonna try to do. But, you know, I mean, if I pick a random B out of here, it's probably not gonna go to 0, right? How can I make it, well, I can't make it go to 0, but how can I adjust it? How many of you seen the TV show Breaking Bad? It's lose my mind, right? You guys worried I'm gonna walk right on you, or Ozark, right? This is like you give B to the mafia and you let them do some laundering for you. We're gonna do a little diagram laundering, right? So take a B here, and what I want to do is I want to take B and I want to throw it over into C, and then bring that sucker back. Well, actually, let me get back in. No, I'm good. So y'all see what I did? I took B here to G and then back. Now, notice that so here's my B, then I launder it by sending it to C and then back. Now, I want you to notice this. If I look at the difference between B and my laundered B, this is GB minus GHG B, right? But this is the identity on C. And that's T. So this is GB minus GB 0. So B minus HGB is in the kernel of G, which is the image of that. That is kind of the key to where I'm trying to get here. Okay, so now I'm going to do what comes naturally, right? There is an A. Actually, I can go further than the statement I made. How can I go further? Not only does there exist an A,
It's unique.
there's only one of them, right? So I'm going to find K of B, the F inverse of B minus H. So I'm actually going to define my K that way. So I guess I should probably try to convince you all this is a homomorphism. Notice that B1 minus H2 B1 equal A1 and K B2 minus HG B2 equals A2. So this means and B2 minus HG B2 equals F of A2. And so the fact that F is a homomorphism this is F of A1, F of A2, which is equal to B1 plus B2 minus HG B1 plus B2. Literally, they're using the fact that G and H are homomorphisms, and their composition is a homomorphism. So K of B1, B2 is equal to F inverse B1 plus B2 minus HG B1 plus B2, which is A1 plus A2 plus KB1, KB2 cubes. So it's an abelian group homomorphism. So as an exercise, see if you can show that it works well with scalar multiplication. Well, and so the final thing is, so K is an R module homomorphism. And so if you look finally at the composition, because the last thing we have to do is show that the composition is the same. If you look at oh, good, there. So if I look at K at A, well, after all, this is F inverse F of A minus HG F of A. Right, isn't that our rule? Right, okay, if this is F inverse of this thing right here. Oh, so crossed here. That- Now, the important thing to notice here is what is GF as I go through the exact sequence. I do F G is 0. So this is F inverse F of A. So we have A positive. Any questions? Okay, so if I had splitting here, then I've got it back. Now I want to show that if I have the splitting here, then I get this sequence as isomorphic, right? Let's do this. M plus C. So we have to sketch this horizontal sequence again. So I know I've got the splitting back here, we've got A, where when you do F, then you do K, it's ending on A. And somehow, you've got to draw this out here, it's a visual aid. So really, our burden here is to build this guy. Right? This is we'll build that makes the diagram commute. I want to go from here to here. Start with B. What do you think? Well, let me give you a hint. A lazy creek. What's the easiest thing to do? Right, I've got a couple of things that I can do that'll shove this where I want. Get into A, I can go KB. Well, give me something that's correct as far as where it lands. And how about here? Just use G, right? And let's just cross our fingers. See if this works. Uh, Anybody like to see me verify this? It's fairly straightforward, right? Because both boards are multiple opposite, right? That's all I need there. Um, first I want to show that okay, so first thing I want to do is I want to show that the kernel of this is 0. So let's let B be kernel phi. So B, so B is KB GP, which is 0. So in particular, I have KB as 0 separately. I have KB B. Oh, B. So GB is 0. Then G, that is to say B is in the image of F. And so okay, but let's see what we do with this. Well, so if I compose this for K, KD is 0, right? This is KB is 0, but this is the identity function on A. So A 0, and so B, which is F of that, is 0. Now, I guess what we want to do is we want to show that it's on to. So let's let A, C, B, work some there on the bottom. Well, since G is on to, there exists B can be such that F is. Right? Now, this is a candidate because I know that in the second coordinate it'll be right, but there's no guarantee. So, so G of B equals C, but K of B may not be A. But so we'll have to adjust this somehow. And as you might guess, I can adjust this by something in the kernel of B, which is the image of A. So let's precisely see how we might go about this. So we can just B by an element. Now, I already played around with this and worked it out. So we will choose so after playing around and trying to adjust this to make it work out, we can, and of course, once we see this, see how it might work. B minus FK of B. Okay, so let's see if this is the appropriate element. Notice that F is a homomorphism. So the difference between B and this thing is in the image of F, which is the kernel of P. So this should actually still be correct on the second chord. Right? Let's look at this thing. FK. Well, what are my rules here? This is K. K B. I said KB FA. And then G, same mess. In the second, well, okay, this is KB minus K F A plus K F A. Right, it's true. So G of B minus G F A of B plus G F A. Right, less. But let me remind you, GF is 0. That's the original exact sequence. So these two are gone. And what else do I know? I know that when I do FK, this is the identity of A. And there's an FK again. So this becomes KB minus KB. And this becomes A. And this is G of B. Which, if you recall, is C, right? KB's cancel out and make it A, C. Okay, any questions? I will let you all check, the diagram. That's not very good. Okay, any questions? Let's finish this up with the C implies A. Okay, so here's the situation. We have this diagram here. What we have. C. A, this is D. But sketches. Difficult to see. Yes, and this is F. G, this is inclusion A, projection on C. The diagram. And what we have to do is get the splitting, right? We have to, well, in fact, we have to get the H splitting. Find. Let's say H. Okay, how am I gonna find this? Okay, here it is. Yeah, in this track. It's just going to five. All right, that's it, right? So, this is the identity, so I don't really need to change it. How do I go back here? Right. So I think the natural way to kind of go back here is go from C, 0, C. And then right. And we'll see what was supposed to happen when I do H and then I do G. So when I do H and then G, it should be the identity. So notice. G, uh, but what else do I know? So I've gotten this far, which is very far. But also, what do I know from the original diagram? When I do G in the identity, this is the same thing as doing phi and IC. Going G is the same thing as going phi and I. Right. So G phi inverse IC. So in conjunction with this, G phi inverse is IC 0C, which is okay. Any questions? Split exact sequences are very, very important all over the place. But here's something that will come up in this context as well. Okay, so in 8510, did you all see the fundamental theorem of finitely generated abelian groups? Right, every abelian group, every finitely generated abelian group, some finite number of copies of Z, maybe you can see that part, but the finite part can be broken up into like invariant factors, element factors. Free modules are important behind that too. Modules are a generalization of vector spaces. And what was the big thing about vector spaces? Right? I mean, one of the cool things about vector spaces is they have bases, right? And you have these things that are like linearly independent sets, and everything in the vector space is a linear combination of this. Free modules are essentially that. Free modules are modules that have bases. And free modules actually are sort of the ancestor, if you will, of all other modules, because as it turns out, every module is a homomorphic image of a free module. So if you understand free modules and you can function out by something, then you've got all modules. So it's not like something pretty important. As you might expect, we're going to open this up with the analog of a linearly set. So let me give you this definition. Let's suppose that we have an R module. And so maybe I'll talk a little bit about unit set later. Now, so empty. Take any non subset. We say that is linearly independent. If given any finite subset x1, x2, n, x, the relation R1 x1 plus x2 R1 n 0 implies Ri equals 0 for all I. So a linearly independent set, I think, is exactly which you would think it would be, it means you have any finite linear combination of elements in that set. If that turns out to be zero, then all your coefficients, all your multipliers have these. If a set is not linearly independent, we say it's linearly dependent. Um, Also, using the notation definition, yeah. Let me make clear that in my continuation definition, I'm not assuming over here that X is necessarily linearly independent. If you have any set, and, remember what this is the intersection of all submodules in containing X, or basically it's every finite linear combination of, elements from X. If this is all of M, we say that X actually spans, M. And as you might guess, maybe, we are going to say a module is free if it has a basis. So let me give you kind of the big theorem in all its glory. We'll talk about this next time. Theorem. What are the identity? You can of course expand this to other more general situations, but right now. And yeah, the unitary. So we go, so assume this R module. Following conditions are filled. Number one, F has a non-empty basis. Let me make clear a linearly independent space. Two, F is the internal direct sum of a family cyclic R modules. Each of which is isomorphic R. I don't make much distinction between 2 and 3, really. F is isomorphic to the direct sum R. So as an R module, it's just some number of copies of R over some index set that might be very large. And finally, here, 4, here is a universal mapping problem. There exists a non-empty set. And a function, which I would call iota from X to F, with property given any unitary R module M and function. I don't mean I'm just freaking function F from X to M. From there, X is just like they said. There exists a unique R module. R module. Says F bar out of it. So in other words, you have the situation here. You have, I think of X as basis, but it's a set function here. There's a function F. This is just a function. Determinants. It's just the diagram. That's one of the things that you probably learned first in linear algebra. Remember how to determine any linear transformation, all you had to do is just tell the basis elements where to go, right? Just list your basis elements and say, you go here, you go here. This is essentially what this theorem says. This is you telling the basis elements where to go. So we'll discuss this more deeply next time. Any questions? Any questions on them? All right, we'll see you all.